In this video, we're going to look at the tails of geometric series. Now, I want to remember that a geometric series is just a series that looks like r to the k as k goes from 0 out to infinity. And that's 1 plus r squared plus r cubed and so on. And we happen to know that if the ratio is less than 1 in its absolute value, the geometric series converges, and it converges to 1 over 1 minus r. Well, what I want to look at in this particular video is the tail of a geometric series. So what does the tail of a geometric series look like? Well, the tail of a geometric series would be the series as k goes from n plus 1 out to infinity of r to the k, and that will be r to the n plus 1 plus r to the n plus 2 plus r to the n plus 3, and so on. And I want to notice that I can factor out an r to the n plus 1. And when I do, this is what we get. And the stuff inside the parentheses is very familiar. This stuff here is exactly the same series that we started with, and as a result, our tail is going to go to r to the n plus 1 times the series as k goes from 0 to infinity of r to the k, and that's going to be r to the n plus 1 times 1 over 1 minus r if we are on a series that converges, and this winds up becoming r to the n plus 1 over 1 minus r. And so geometric series have tails that are very easy to find. In a geometric series, the tail is always going to be equal to r to the n plus 1 over 1 minus r. Well, let's see what this does in practice. So I want to look at a couple of problems. And the first problem that I want to look at is going to be dealing with the series 1 over 3 to the k as k goes from 0 out to infinity. That's nothing more than the series as k goes from 0 out to infinity of 1/3 to the k. And what this means is that we've got a geometric series and the ratio is equal to 1/3. Now, my first question is going to be, suppose we use S4, which would be 1 plus 1/3 plus 1/9 plus 1/27 plus 181 to approximate the whole series. I want to know how accurate is the estimate. And I do want to point out that this guy here is S4 because this is k is equal to 0. This is what happens, what we add when k is equal to 1. This term is the k is equal to 2 term. This term is the k is equal to 3 term. And this is the k is equal to 4 term. Remember that when a series starts somewhere other than 1, the Sn is just adjusted by whatever the starting thing is. So this really is S4. Well, how accurate is this estimate? Well, to get an idea on that, what we want to do is we want to look at the tail for that S4 estimate. We want to look at the tail r sub capital 4. Now that's going to be the series as k goes from 5 out to infinity of 1 over 3 to the k. And as we've just seen, that's going to wind up being 1/3 to the 5th over 1 minus 1/3. And when we get the arithmetic dealt with, we are going to have 1 over 3 to the 5th times a 3 over 2, because this chunk here, that's equal to a 2/3. And when you invert and multiply, this is what you get. So this is the result that you get after invert and multiply. So R4 looks like 3 over 3 to the 5th times 2, and that gives me a 1 over 3 to the 4th times 2. That's a 1 over 2 times 81. That's a 1 over 162. Now, that's the actual error, but to give ourselves some kind of little easier way of thinking about what this means, I want to kind of trap 162 between two easy numbers. It's certainly bigger than 100, and it's less than 200, and that's going to tell me that 1 over 100 is certainly bigger than 1 over 162, which is bigger than 1 over 200. And so what this is telling me is that the error in using S4 to approximate stuff is going to be less than 1 over 100. That would be less than 0.01. So we definitely have one decimal place worth of accuracy, but not 2. This is certainly less than 0.05. So we do get 1 decimal of accuracy in this estimate. Now, I want to look at a second question on the same basic kind of series. So we're going to stick with the series of 1/3 to the k as k goes from 0 out to infinity. And this time the question that I'm going to ask is this: how many terms do we need to add together to get an estimate that is accurate to, let's say 3 decimals? Well, to answer this question, what I want to do is I want to look at things this way. In order to have 3 decimal places worth of accuracy, so 3 decimals of accuracy, what that says is I need my error to be less than 0.1235. That happens to be 5 times 10 to the minus 4th. And so what I need is I need to find an n such that the tail is smaller than 0.0005. And what that means is I need, since I know that the Rn in our case is 1/3 to the n plus 1 over 1 minus 1/3. The Rn is 1 over 3 to the n plus 1 times that 3 halves. Remember that 3 halves is coming from the fact that this bottom is equal to 2/3. So when we invert and multiply, we get the 3 halves. And this simplifies to 3 over 2 times 3 to the n plus 1. And that's going to simplify, when we cancel those 3's out, we're going to get 1 over 2 times 3 to the n. So what this means is that we need to find an n such that 1 over 2 times 3 to the n is small enough, and our desired error is 0.0005. Now this is obviously either a calculator problem or a Mathematica problem, and because I happen to be on a computer and I'm better with Mathematica than I am at a computer, I'm better with Mathematica than I am with a calculator, we're going to look at a Mathematica notebook. So we're going to look at a Mathematica notebook now. So let me get into Mathematica. And what I want to do is I want to first of all create a function that's going to be that tail. And we're just going to use the same notation of capital R. So capital R of n needs to be equal to, let's see, it turned out to be 1 over 2 times 3 raised to the n. That happens to be what our tail is. And what I want to do is I want to look at a table of values, and I need to know what n I'm on and what the remainder size is. And let's just start with what are the first 10 tails. Now, one thing that I notice right away here is that we've got exact fractions. And gee, I did the first 190 tails. I don't need that many. Let's do the first 10 tails. These are exact fractions. And that doesn't really help me very much because I'm not very good at converting decimals to fractions in my head. So I'm going to make Mathematica do that for me with the capital N command. So we hang out capital N around the tail, and here are the actual numerical values for those tails. And I'm looking for a number, an R of n number, that is smaller than 0.0005. 6 is not quite small enough because the tail with 6 terms is 0.0006. But if I go out to 7 terms, if I go to S7, the error becomes 0.000228,624. So we're going to call it 229 and some change. That's small enough. So what I know from the little bit of Mathematica or calculator work is I know that when n is equal to 7, the tail of the series is 0.000228 ... And that's certainly smaller than my desired error. And so what does this say? Well, what this actually is saying is it says S7 is accurate enough. Well, let's just continue looking at things to make it just a little bit clearer. Since S7 is accurate enough, what that really says is if we use S7, which would be 1 plus 1/3 plus 1 over 3 squared plus 1 over 3 cubed plus 1 over 3 to the 4th plus 1 over 3 to the 5th plus 1 over 3 to the 6th plus 1 over 3 to the 7th, this number, whatever it turns out to be, is accurate to 3 decimal places as an estimate for our infinite series as k goes from 0 out to infinity of 1 over 3 to the k.